Thank you. So this talk is about data and pointer prioritization for scalable protection against data-oriented attacks. So as most of you probably know, with the state-of-the-art defenses, especially the control flow integrity, the control-oriented attacks have become sort of unreliable. So this is why in recent time we have seen an uptick to the data-oriented attacks. So why is this shift? This is because the data-oriented attacks are also a class of powerful attacks that do not violate the normal flow of a program. That means the CFI countermeasures won't work for this kind of attacks. Also, these data-oriented attacks has the similar level of expressiveness as control-oriented attacks, and apparently no practical defense mechanism to prevent these data-oriented attacks. So why are the existing defense mechanisms not practical? So the key attack strategy for data-oriented attacks is the manipulation of data object or pointers. So in order to prevent data-oriented attacks, we need to ensure the integrity of the data or pointers. And it takes a high overhead to do this kind of data integrity, primarily because the huge number of data objects and pointers in a program. So then the fact is it takes high overhead for existing defense to prevent the data-oriented attacks through data integrity. So then we made an observation that in an application, not all the objects or their pointers are vulnerable or equally sensitive. So from that observation, we thought, what if we discard or filter out all the insensitive data object or pointers from an application and prioritize only the sensitive ones for protection. So from that thought, we proposed this data pointer prioritization or DPP framework that automatically identifies the sensitive data object and pointers from a program and prioritizes them for protection. With three key criteria in mind: it needs to be generic, adaptable, and capable of being integrated with existing defenses so that we don't need to re-implement or implement any defense mechanism. So this is the framework of the DPP. So the idea here is that all the attacks need some entry points, so which is basically are the external input sources. So we identify all the data from these external input sources, taint them, and propagate those taints throughout a program using data flow analysis. And after that, we perform our prioritization on top of those tainted data flow graph, which gives us a list of sensitive data object or pointers. And we can then feed this list of sensitive data object or pointers to existing defense for protection. And in this work, we used a rule-based heuristic to guide the prioritization. So once we say rule-based something, the first challenge that we need to overcome is how we can obtain a representative set of rules with comprehensive coverage. So the way we solve this challenge is that we break down the exploit strategy into smaller components, and then we deduce our rules from those smaller components. It has two benefits. First, those smaller component, the rules from the smaller component is common enough to be present in multiple exploit. And second, it has the potential to anticipate future exploits. The second challenge is how we can evaluate the accuracy of these rules, because we see there is no ground truth data set that indicate us these are the vulnerable list of data object or pointers. So we had to manually curate this information from existing vulnerable programs. So these are the 7 rules that we extracted for this DPP framework, which basically deal with data object or pointers used in predicate that may alter program behavior, data object or pointer used in loops that are near data buffers, the data object or pointers that are used in vulnerable function that have been casted into different types, and also the data object that have out-of-bound access or data pointers that have been allocated with an unbounded conditions. So we, as I said before, we applied our rules on top of a tainted data flow graph, and we use an existing open source tool called Static Value Flow, or SVF. So this SVF tool can construct static value flow graph on top of LLVM IR. But it had some missing dependencies specific to our task. So for example, if an index of an array is tainted, then we want the array to be tainted as well, which is not captured in the default SVF graph. So we had to implement those sort of features, dependencies in this SVF graph. So this is an example of a tainted data flow graph that has been constructed using the SVF tool, where the taint started from, in this case, from the argument of main and this size field. So once we have this tainted data flow graph, we implement our rules on top of it. We implement each of our rules as an LLVM analysis pass. For rule 1, 2, 4, and 5, which basically deal with data pointers or object in predicate loops and vulnerable functions, or that has been casted into different type, we needed to perform alias analysis, loop analysis, and we needed the data layout information from LLVM. These rules are relatively easier to implement compared to the other rules. For example, rule 3, which is data pointers that follow data buffer, we needed to check all the allocations in a function, or we needed to check all the global variables for data buffers followed by a pointer. For rule 6, which basically deals with the out-of-bound access, we extract all the object or pointers from load, store, and call instruction. Then we apply some optimization. Basically, we filter out all the safe memory object or pointers using stack safety analysis and size and offset approximation, and we leave the rest as sensitive. For rule 7, which is basically the unbounded allocation, we needed to identify all the allocation sites from this SVF graph. Then we convert this allocation node into its corresponding CFG node in order to backwardly search for the compare instruction. But it has some challenges. We had to solve these challenges using some simple mechanism, as well as we proposed some new mechanism like common ancestor. But I'm not going to go into details of this. We can find the details in the paper. So in order to evaluate our framework, there are some other evaluation, but these are the two key evaluations that we performed in the paper. So the first one is how capable and effective is DPP for prioritizing and ranking security critical data. And the second one is how much performance improvement can we gain using this DPP framework. So for this, we used AddressSanitizer. And for the setup, we use we prepared 3 versions of a program. The first one we call baseline with no instrumentation. The second one is AddressSanitizer, or ASan, where we instrument all the object in a program. And the third one is ASan plus DPP, where we use AddressSanitizer to instrument only the prioritized data object. So for the security evaluation, we wanted to see how the AddressSanitizer with DPP perform. So basically, we wanted to see whether AddressSanitizer with DPP can detect all the memory errors from Linux Flaw Project and Juliet Test Suite, the same as the default ASan can do. And we found out that the ASan with DPP can do the same as the default ASan can do, but only with protecting the prioritized data object. The second evaluation, we want to see how much effective our prioritization is. And for this, we extracted 16 vulnerable data objects from 13 applications. And we saw we can find these 16 vulnerable data objects on the top 5% of our prioritized data object, meaning that if we want to, if we leave the rest 95% data objects, we can protect these 16 vulnerable data objects. So for performance evaluation, we use the SPEC CPU2017 Integer benchmark, and we protect all the prioritized data object. And we can see that DPP can improve the performance by around 1.6 times. We can also see that DPP can reduces the runtime overhead by around 70% compared to the address sanitizer. So we have some limitation. So as you can see, we used address sanitizer tool in our prototype. That means it is not a live defense yet, but we are working on it to make this defense live. Also, in one of our rule, we consider only the data pointers followed by a buffer, but that is equally true for other sensitive variables. So we are in a way to incorporating that change in our work. And for the benchmark or evaluating the effectiveness of our rules, we still believe a broader benchmark still needed for fully assess the effectiveness of our rules. So in conclusion, we proposed a framework for automatically identifying security critical sensitive data object or pointers from program. And we see that simple rule-based heuristic are effective enough. But we are not claiming that our rules is OL representative with all the comprehensiveness. We are still believe that we need to make change in the future to incorporate any new rules to make the set of the rules OL representative. And also this kind of prioritization scheme is sort of new into the system security literature from the conventional protection paradigm. So our source code is available, and with that I'm happy to answer any questions.